A team of observatories, including NASA's SWIFT satellite, recently joined forces to trace a hard-to-detect cosmic particle back to its dramatic origin. The particle, called a high-energy neutrino, was likely produced by a tidal disruption event, which occurs when a star passes too close to a black hole. There, extreme gravity causes the star to bulge and break apart into a stream of gas, with some of the material swinging around to form an accretion disk. Neutrinos vastly outnumber all the atoms in the universe, but they have almost no mass and rarely interact with other matter, so they're very hard to pin down. However, scientists have detected them coming from extreme objects like exploding stars. High-energy neutrinos come from even more bizarre places, like superfast particle jets driven by supermassive black holes. Scientists suspected that tidal disruptions could also produce high-energy neutrinos, but they weren't sure where or when in the process the particles might appear. Some suggested powerful jets would create these neutrinos. Regardless of how they're made, though, astronomers expected they'd appear early on, when the event is brightest. However, a high-energy neutrino arriving from a tidal disruption called AT 2019 DSG offered new insights. An observatory called the Zwicky Transient Facility in California discovered the event in April 2019, but it wasn't until October that the IceCube Neutrino Observatory in Antarctica detected a high-energy neutrino astronomers linked to this event. Measurements by SWIFT and other observatories showed that the tidal disruption's visible and ultraviolet light peaked and appeared to plateau, and its X-rays dimmed quickly. However, radio telescopes saw its emissions steadily increase. This meant that some particles were being accelerated even though superfast particle jets were never detected. So, AT 2019 DSG had the right environment to accelerate particles and produce high-energy neutrinos, and maintained it for a longer period than scientists expected. Astronomers think the neutrino may have come from one of three regions: in the disk close to the black hole, where particles colliding with X-rays could produce neutrinos; further out in the disk, where particles could interact with UV light; or in broad outflows, where particles could collide with each other. This is only the second time a high-energy neutrino has been tied to a source beyond our galaxy. Scientists are searching for links between previous tidal disruptions and other high-energy neutrinos. And, as observatories discover new events, they now have a better idea of where and when they might find these elusive particles.